Hello everyone. We are starting a free open lecture on our Discord. If you are a viewer and want to ask questions and get answers online, join our lectures. You can find the link to Discord in our Telegram channel. Now, let's move on to the code itself. Let's take a look at the code. The code seems very cumbersome, but in reality it is very simple. Let's look at the first function. This is the function that we will be calling. It is the merge sorting function for arrays. We have an array, and we call the split function on it. This is our initial action which splits the array. It then returns the merged array. So basically there are two actions. First, split, then merge. Now the question arises, how will it actually split? And so we turn to this. Split the array. So, accordingly, split the array. If the array length is 1, return the array itself. Otherwise, the first half and the second half split the array in half, meaning it also splits it in half and calls the split function itself. This way, as you can see, it calls to return the array up to the middle and the array from the middle to the end. It just takes two halves regularly and splits. There will be logarithmic splits. This is exactly what is written here. The next function we call is to merge. It calls the array, and what it does is we get the final array, which will initially be empty. If the array is odd, add an empty array. We add an additional array to throw in one of the elements for evenness. It's just that when we have an array, for example, with a single element, it can't just remain as a single element. We need to ensure that there is an empty one. In any case, if an array, for example, of one element is combined with an empty array, it will result in an array of one element. This is done to ensure there is an even number, making it easier for us to handle. Accordingly, it calls the array to add an empty array from 0 to the length of the array minus 1 in steps of 2 because it pairs the elements, and it sorts these arrays. The final array adds the current one. So, the question now is how it sorts. Here it is said to sort the array. It sorts using the algorithm we discussed. We have the first array and the second array, which come from the arrays I and j equal to 0 and the new array initially empty. We will be adding values to the new array. While the length of I is less than the length of the first array, and j is less than the length of the second array, if the first array with index I, that is the 0 element of the first array, is less than the first element of the second array, yes, that is under the j index. In this case, we just add the first element from the first array to the new array, and then move it. Otherwise, we add the new element to the second array, also j, and j is incremented by 1. Accordingly, we have covered this part, and these are the two tails exactly. These are two tails. And when we are left with one of the tails, we simply start adding these elements to the new array. Some sums, adding 1, subtracting 1, and for example, adding two other numbers, will not affect it at all. Obviously, the logarithm, if we take n as 10 more 9 and k as 10 more 9, will result in only about 30 operations. Well, actually not 30, I think it's 29.
Want to become a great programmer? Subscribe to our Telegram channel.
So here, if we take 10 to the power of 9, then it will be 10 to the power of 9 here, 10 to the power of 9 here, and it will be 10 to the power of 18 overall. So obviously it's 2 times 10 to the power of 9, and here it will be approximately 32, I suppose, but I can't say for sure. It needs to be calculated, so obviously here it will be 10 to the power of 18 multiplied by 30. This is the most powerful coefficient of the sum, which is why we say that the complexity of this algorithm depends on this coefficient of the sum. Again, we cannot disregard either n or k from this, and we can only take this because, for example, we also have a dependency on n here, just like here. And obviously, this dependency is several times greater. But if I had already substituted some number q here, then I would say that this sum plus the logarithm base 2 of q. Why? Because there is no q here. I have nothing to compare the complexity of q with, therefore I cannot speak so definitively. What I can discard is this complexity. If I have a cube that is around 10 to the power of 150, it is obvious that the coefficient there will be not small. Therefore, I must also take this complexity into account and accordingly leave the maximum complexities with some coefficients that I have. And let's consider the second example. We also have n plus n multiplied by the logarithm of n base 2. So if I take this and sum it up, I can rewrite it and, for example, factor out n as a common factor,
then in the parentheses I will get the logarithm of n base 2 plus 1. It is obvious that this plus 1 operation, even though it occurs in times, yes, compared to the logarithm, for example, if we have 10 or 18 as the logarithm, what will we get? Well, 60, yes, somewhere around there, probably a little over 50. So we will have that here, it's 50 plus 1. Obviously this one doesn't have a significant impact. Therefore it can be disregarded, so the overall complexity of the algorithm in this case will be n times the logarithm of n to the base 2. Again, asymptotic complexity is not intended for calculating the most precise definition there. It exists to determine the approximate complexity of work in the worst case. That is why we consider the worst case of the operation of a certain algorithm or block. It is precisely because of this that now let's calculate on some simple algorithm. Even if you have the code for the task, you already understand something about it in advance. Let's try to evaluate the complexity of this task. It is obvious that assigning a value to A is just one operation, which is constant. There is no dependency here. Next, we have a for loop that runs in times, so it is clear that there will be a dependency on n, which indicates linear complexity. There are no logarithms here. Then we have an index calculated using some binary search, and the complexity of binary search is O log n base 2. So we will write it down like this. Furthermore, we have a plus bound 1, which again does not depend on anything, so it is constant complexity. Next, we have print A, which also has a constant complexity. Therefore, if we sum all of this in big O notation, that is 1 plus n plus logarithm plus 1 plus 1, we understand that the 1 can be immediately disregarded because it is constant when we have large coefficients. And we will simply get on plus the logarithm of n to the base 2. Here we can understand that the coefficient of 2 depends only on n, referring to the coefficient of the sum, and which one of them is greater, simply. It is obvious that if we take n as 10 to the power of 9, then the logarithm will be only 30. This means I can disregard this complexity because for some large n, this complexity won't carry much weight. So I can simply say that the complexity of this logarithm is O of n, because the logarithm operates significantly faster than any linear complexity at some number. So I can say that the complexity of this code is indeed. We will have OATN. Thank you very much indeed for listening to the lecture. We are all waiting for you next week in our Discord for the online presence at our lecture, where you will be able to ask questions.
Want to become a great programmer? Subscribe to our Telegram channel.